Hello, and in this video today we're going to be looking at hydrostatic pressure and a manometer. So for this problem it says a U-tube manometer is connected to a closed tank containing air and water. So first we're going to draw our picture. So we have our tank with some amount of water and air, and it's connected to a U-tube manometer. So we're going to have that, and this manometer has some amount of fluid in it that stops and ends at these 2 points. So we're just going to fill all that up. So we know that it's a different material than water, but it's still a fluid. So we know that it's closed end, so it says at the closed end of the manometer, we know that the pressure of the air is 16 psi. So we have a little gauge here that's recording this for us. So this we know is P air is equal to 16 psi. So I'm actually just going to make these red so we can differentiate all this information. And then we're going to say determine the height differential of the gauge fluid with a specific weight of 90 pound force per feet cubed. If the height of the water is 4 feet above the pressure gauge for the tank and its pressure reading is 4.3 psi. So it's basically telling us, look at the difference of these two heights right here. We're going to call this H1. And then it tells us the specific weight of this fluid, which is Y or equal to the squiggly thing right here. Your book will write it as Y, but we normally make the squiggly. It's whatever you prefer. But we know that it's 90 pounds of force per feet cubed. And then it tells us if the height of the water is 4 feet above the pressure gauge for the tank. So somewhere down here is some little gauge, just like the one up here, and its difference of height, well, let me make this red again. We're going to call this H2 is equal to 4 feet from the top of the water. And then it tells us if this gauge down here has a reading of 4.3 psi. Now remember, this is an atmospheric pressure, and this is a gauge pressure. We'll have to remember that whenever we're doing our calculations. Now, what we want to do is pick our points for how we're going to determine our equations. So you normally want to pick the starting and stopping points of the fluid. So we have point 1, we have point 2, and then the other fluid that we're going to want to look at is water, because that's what we're given other information for. So we have point 3, and then down here, we're just going to call this our gauge pressure. Well, we know from hydrostatic pressure that as the height increases, pressure must go down. If pressure is greater above something, then it's going to crush it. So pressure must go down as we increase in elevation. Think about how the pressure at the top of Mount Everest would be a lot less than the pressure on ground level or at sea level. So we're going to want to create our equations here. So we know that the general idea is the pressure of the lower is equal to the pressure of the higher point plus the density of whatever's between them times gravity times the height between them. That is their basic equation we're going to use. So we know that P2 is equal to P1 plus rho of whatever the fluid is times G times the height between them. Well, we know that density times gravity is equal to the specific weight. So then we also know that P1 is equal to our P air, because we were given this reading of the gauge up here. This gauge is reading all the air in here and telling us that pressure, which is 16 psi. So we're going to plug these in. So we know that P2 is equal to P air plus the specific weight times H1. And then we're going to look at these two right here, because this is what we were given information of. So the top of the water and the gauge. So the pressure of the gauge is equal to P3 plus the specific weight of water. So again, I'm just using this identity. The specific weight of water. So I'll say this is the fluid and this is the water times H2. And then, but how do we relate these two equations? Well, this tells us that we can neglect the weight of the air in the columns in the manometer. So this little height difference right here, whatever H3 may be, is negligible. We can say that's equal to 0. So we can really just say that P2 is equal to P3. So if we rearrange these equations, so let's rearrange this equation so we can say what P3 equals. Just subtracting this over here, we can get that P3 is equal to the gauge pressure minus the specific weight of water times H2. Now we can put these equal to each other. So the air pressure plus the specific weight of the fluid times H1 is equal to the gauge pressure minus the specific weight of water times H2. And now let's start plugging in our information. So we have 16 psia plus 90 pound force per feet cubed times H1 is equal to our gauge pressure, which is 4.30, and it says psi, so pound force per inches squared, minus the specific weight of water. Now, what is the specific weight of water? We know that density times rho is equal to the specific gravity. The density of water is 1.94 slugs per feet cubed. Now, let's get the density in pound mass. We know that one slug is equal to 32.2 pound mass per slug, or we'll just say pound mass. So if we use this conversion, so we do 32.2 pound mass per slug, we get that density of H2O is equal to 62.4 pound mass per feet cubed. But then, so when we multiply this by gravity, so we have rho H2O times G is equal to 62.4 pound mass per feet cubed times 32.2 feet per second squared. For English units, that is the specific gravity constant. Well, this would give us something a lot greater than 62.4, which is what the specific weight of water is. Well, why is that? So we also need to know that 1 pound force is equal to 32.2 pound mass feet per second squared. So just like how 1 Newton is equal to 1 kilogram times meter per second squared, it's the same idea just in English units. So 1 pound force is kind of the same thing as a Newton here. It's a mass, so I'm going to do this in green. So it's a mass times an acceleration. Okay, so going back to our density times gravity, we have 62.4 pound mass per feet cubed times 32.2 feet per second squared. Well, then we have to say that 1 pound of force, sorry, the thing gets kind of thick and I don't like drawing with that. So 1 pound force is then equal to 32, man, 32.2 pound mass times feet per second squared. So this is what causes these 32.2s to cancel out. And this gives us that the specific weight of water is then equal to 62.4 pound force per feet cubed. And of course, you can then just say that's 62.4 pound per feet cubed. So going back all the way up here, I'm going to say this is 62.4 pound per feet cubed times our H2, which is 4 feet. So this is 4 feet. Now we're going to take this right here, go all the way down here. And so we have 16 psia. Well, like I said, that's an absolute pressure. So we need to subtract the atmospheric pressure. and 1 atmosphere is equal to 14.7 psi. So minus 14.7 psia will give us 1.3 psi, which is equal to 1.3 pound force. Remember, pound force is equal to lb. It's the same exact notation per inches squared. So now we have everything in similar units, just about, but we'll get to that. And now we can start subtracting and adding things. So we have 1.3 pound per inches squared plus 90 pound per feet cubed. So you can see where I'm going to go with this. H1 equals 4.30 pound force per inches squared minus 62.4 pound force per feet cubed times 4 feet. So we can subtract the 1.3 over here, and we'll get 90 pound force per feet cubed times H1 equals 3 pound force per inches squared minus, and 62.4 times 4 feet is 249.6 pound force per feet squared. Now, you don't have to write all the units throughout this entire thing, but whenever you start converting things, you're probably going to want to write it. So normally I would just not even write these like feet squared and stuff because I know that's what it's at. But I would write this because we're about to convert this. So we can tell that if we divide the 90 pound force per feet cubed, that it's not going to correctly work because this is in inches squared. So we need to convert that real quick. So 3 pound force per inches squared, there's 144 inches squared and 1 foot squared. So 1 foot is equal to 12 inches. If you square both sides, then you get 1 foot squared is equal to 144 inches squared. But this will give us 432 pound force per feet squared. So now we have all the things in the correct units, and we can start to solve this. So if we take H1 is equal to 432, and now that they're all in the same units, I'm just not going to write them. 432 minus 249.6, all of this divided by 90, we get that H1 is equal to 2.03 feet. And that is how you solve this problem. Obviously, a lot of this work is just explaining it, but so you wouldn't need to write all of this down, all the steps, drawing the arrows and all this stuff. But that is how you get your answer. Now, I want you to think about it for a different kind of problem. You might have to solve for this gauge pressure down here, or you might have to solve for this height, or maybe it'll ask you what the specific weight of this, but you're using the same concepts. You're going to be setting up these equations and balancing them out, and then you're going to be plugging in your numbers and changing them around, changing the units, always be watching the units, and you will get your final answer.